Okay, let's look at this problem of two blocks hanging from a pulley. Notice that the cord in this case is massless and the pulley is massless and frictionless. So we just aren't ready yet to bring on some of the other complexities. So right now we are looking at this as simply as possible. The mass of each block is given 3m and m there, and what we're asked to determine is the speed, notice speed of each block at some time t prime after the system's released from rest. Okay, so we need to handle this. This is a force analysis problem, so I know the tools at my disposal here are going to be free body diagrams, which is cool. So first I'm going to look at the system and I'm just going to try to get a feeling, if I can, for what the system is doing. And I always want to ask myself, is it accelerating? And if so, how is it accelerating? So I can look at these masses, the 3m and m mass, and I know when I release the system from rest that my 3m mass is going to accelerate downwards, right? And my m mass is going to accelerate upwards. So I can see the directions of those accelerations there. And I'm going to take that into consideration when I do my force analysis. So let's go ahead and draw our free body diagrams and just kind of go from there. So my free body diagram for the 3M block here. Let's look at what we have. We have the tension, what's touching the block. There's a string, a cord attached to the block. So that cord is going to exert tension. I'm just going to label that T upward on the block. And then I have my one invisible force, of course, and that is the weight of the block. I'm going to call that weight. Actually, here I'm gonna go ahead and put in the magnitude of the weight since I think that'll be better for notation here. So when I'm calculating weight, of course, the equation for calculating the weight is an object's mass multiplied by gravitational acceleration, or little g. So for this case here, I'll go ahead and put in the object's mass, 3m, and then that is multiplied by little g, gravitational acceleration. Try to, if you have fallen into the habit, sometimes people have, due to high school physics or other kind of exposure, of calling that lowercase g gravity, try to get yourself out of that habit. That's not really being scientifically literate, and the language that we use represents ideas, and our brain listens to the way we speak. So, if we can try to use correct terminology and speak correctly, that will help our understanding. These are the only two forces on this particular block. Now, this block is accelerating downwards, and in a previous problem, what I had told you is my advice always is to have positive be in the direction of acceleration. So for this block, for this free body diagram, I'm going to go ahead and say that positive is downward. Okay. Now let's do the next free body diagram. That is for my block M, and I'm going to do a similar thing here. We only have vertical forces in this case. So I have tension upward due to the cord that's attached to it. If I look at that block, I ask myself, what's touching it? Just the cord. Tension upward, and then its weight downward. And weight in this case is its mass, which is just m, multiplied by g, gravitational acceleration. So one question here is that you can might see that I have drawn the two tensions, or I've written the two tensions using exactly the same symbol. I didn't subscript those T's, and you might be wondering, can I do that? Are those the same? They are the same as long as we have this massless, frictionless pulley here. And we actually will not have the physics, we will not be ready to deal with pulleys with mass until closer to the end of the quarter when we get to rotation. So all our pulleys for the time being for this chapter and the next chapter are going to be massless pulleys. What that means is that the pulley itself does not change the tension. I'm going to say that again. So the pulleys that we deal with for chapters 5 and 6 are going to be massless pulleys. And what that means is that those pulleys do not change the tension. The tension is the same on both sides of the pulley. All right, going back to this case here, now block M is accelerating upward. So I'm actually going to say upward is positive for block M. And you might say, isn't that using two different sign conventions for one problem? Not really. Not really, because of how this problem is, how the system works here. And that is when one block accelerates downward, the other block accelerates upward. You can consider this to be somewhat like if the two blocks were tied together and on a horizontal surface. It's just that the pulley is instead allowing for a change of direction of the cord. Okay, so don't let that get too much in your way. And it part of that is the power of the free body diagram and the analysis that we do there. So we'll go ahead and sum our forces then. If I sum for the 3M case, I will get positive. So let's see, let me do some notation here so you can kind of keep track of what I'm doing here. So if I'm going to sum forces for the 3M case, I've got 3mg minus tension is equal to the mass of this body, which is 3m, multiplied by its acceleration, a. All right, I'm going to do the same thing for the M block here, a second law statement. And now upward is positive. So I've got tension minus the weight of that block is equal to that block's mass multiplied by its acceleration. Now, the acceleration magnitudes are the same for these blocks. This cord is an inelastic cord. It's not stretchy. That means that the blocks will move together. So their acceleration magnitudes will be the same. We've already taken into consideration that their acceleration directions are different. We've done the directional analysis in our free body diagrams. So now we've got two equations, and it's a good moment probably to pause and ask ourselves, how many unknowns do we have? So let's do that real quick. What are our unknowns here? Tension's not known and acceleration's not known. So really we just have two unknowns and we have two equations, so we're good to go. Um, so then your attention might go back to like, hey, wait a minute. This problem is asking us to determine speed here. And what's going on? Well, speed is the magnitude of velocity, right? Velocity is a kinematic quantity. And what is the one kinematic quantity you see in front of you right now? Acceleration. So what that tells us is let's focus in on determining the acceleration. Once we have the acceleration, this problem gives us a time, we can then determine the speed or magnitude of velocity. The velocity directions would be different. So this problem is just asking us for the speed here. Um, so there are some different ways to go about your algebra. I'm going to leave that to you. You can see one way to do it in the written solutions where I go through a lot of steps. You can, again, take your algebra as personal, take the route you want to take. What you know here is that you have two equations and two unknowns. So you're good to go. You have two unknowns, you have two equations. So that's check. We're ready to rock and roll. If you do your algebra here, what you'll notice is that you solve for, so I'm just going to say here, you're going to do your algebra and then you're going to solve for acceleration. Acceleration is equal to g over 2 in this problem. That's what you end up getting for acceleration. I would pause here for a moment and ask yourself if this makes sense. You could consider that, well, it would be less than g, right? It would be weird if you got 2g. I'll let you think about that for a moment. Kind of consider the two blocks hanging over the pulley. So it does make sense that we would get something that's less than G. Would I know looking at this problem from the outset that it would be exactly G over 2? No, but that's okay. You can just kind of pass it through your filter. Does it make sense that it's less? Now let's go ahead and try to finish the problem here where they want us to determine the speed. So what this means is we have acceleration, we have time. We know that we're starting from rest, right? The system, we're told the system is released from rest. And so we want to find the final speed. Well, we have an equation for that. We have velocity with respect to time. V equals V naught plus AT. That's my general equation for velocity with respect to time. So if I'm interested in finding that final velocity, then I will be substituting into that. So my final velocity that I'm looking for, speed here, it starts at 0, initial velocity is 0. The acceleration here is g over 2, and the time I'm given is this time t prime. So my final answer here for my final speed, and I'll just give this positive, they're just asking for a speed here, is going to be 1/2 g t prime.